So sticking with thermochemistry, the next thing we are going to talk about is heat of neutralization. This is the heat change when 1 mole of H plus ions from an acid reacts with 1 mole of OH minus ions from a base. So hopefully the word neutralization is not new to you. Neutralization that we've looked at before is when an acid and a base react together to give a salt and water, in this case the salt being NaCl, sodium chloride, and giving us water as well. A neutralization reaction is, you can identify it pretty simply. It's an acid and a base, the acid supplying H plus ions, the base supplying OH minus ions to produce water. Neutralization reactions are nearly always exothermic, so you can assume every neutralization reaction you come across is exothermic unless you're told otherwise. And the units are the same as for heat of combustion and heat of reaction. It's kilojoules per mole. Breaking it down just another bit to show you how I went from HCl and NaOH to H plus and OH minus. If we break this example down into its ions, so if we separate everything out into ions, H plus and NO3 minus from the nitric acid, potassium and the hydroxide ion from potassium hydroxide, and if we then separate up our salt into its components on the other side, you can see that just like in maths, if you've got something on one side of the equation and on the other, they'll cancel each other out. So you can cancel out all the ions there, and what you're left over with is a H plus and OH minus, and they're making water. So that is our heat of neutralization. So there's an experiment that goes with this. It's to determine the heat of reaction or heat of neutralization of hydrochloric acid with sodium hydroxide. So it's a reaction of hydrochloric acid and sodium hydroxide and measuring the heat changes. It's usually coming up in question 3, so that's where you're looking out for it if you want to go and try some exam paper questions before I assign them. There's an experiment on it, the video of the experiment from our very exciting folks. We'd usually watch if we can't do an experiment. They have that video up on YouTube, thankfully, so you're not missing out there. This is the link for it, but it's also part of the playlist. If you go on to the YouTube channel, it's also in the playlist for chapter 21. So I'd recommend having a look at that. There's only so much talking I can do about it, which I'm going to do now, but it's best to spend a couple of minutes. It's a short one anyway, so I'd recommend just going over and having a look at that. So you've got HCl reacting with sodium hydroxide. They're mixed together in a polystyrene cup. Polystyrene is good for this as it has good insulating properties. We have a lid with a small hole to securely fit in a thermometer so we can register the temperature change in the solution. And we've got a stirrer here so that we can make sure the mixture is uniform, because obviously we want to make sure that it's mixed so that all of the heat produced in the reaction is not in one place in the cup. It needs to be uniform throughout. And then we're going back to, I don't think I've mentioned it before actually. I definitely have, sorry. So the heat given out then is using this equation that we're looking at here. The mass of your reactants, the specific heat capacity, which is going to be given in the question, multiplied by the rise in temperature. So the temperature that these two were before compared to the temperature they were after. Specific heat capacity of water is that, just so you're aware, that's nearly always given to you in the question. And the definition for it, what it is that it's the amount of heat required to heat 1 kilogram of a substance by 1 Kelvin, 1 degree Kelvin. And it will always be given in the question, unless, like everything, there's always an exception. Sometimes the heat capacity of the overall system will be given. And all that means is that the mass, as I've underlined here, has already been factored in for you. So that instead of here having to look at your mass times specific heat capacity times temperature, it's just using the heat capacity of the system multiplied by the rise in temperature. So again, it's the specific heat capacity is just the amount of heat required to heat 1 kilogram of a substance by 1 degree Kelvin. Other notes on this, you will need to know density, and it's nearly always mentioned in the question for you, but if not, you assume that it's equal to the density of water. So in the lab, if you're told to get 100 grams of water, you don't need to measure it out using a mass balance. You can just get 100 centimeters cubed of water. The density of water is 1 gram per centimeter cubed. So that means 1 gram of water is the same as 1 centimeter cubed of water. And we're always working in kilograms for this, so that's why it's written there in kilograms for you. If the acid and the base have different temperatures in the beginning, so we need to look at the temperature in the beginning and to take that from the temperature at the end to find the rise in temperature that's needed for this equation. If the acid and base have different temperatures in the beginning, you should use the average temperature. So you should assume that when they're mixed together, because it's the same amount of each one, that the temperature will be the average temperature. If a question comes up where a diprotic acid is used, so here in this reaction we were using hydrochloric acid, that's HCl. Diprotic means 2 protons. So if you were given a question to do a calculation with sulfuric acid where it's H2SO4, diprotic, then your final answer that you get should be divided by 2. Because remember, just flicking back here, your heat of neutralization is the heat change when 1 mole of H plus ions from an acid reacts. So in a diprotic acid, you're going to have 2 moles of hydrogen ions there. So just to note that. This is the question I'm going to go through in the next video. Just to keep them short and sweet, I'm going to stop here. This will be in the next video. You can try the question yourself if you want to work your way through it. It's from page 375 in the book. There's not a lot of questions here, so I've taken one that they've worked through in the book and I'm going to talk you through it as well. I don't want to take, I think between the workbook and the textbook, there's only one question for you to do on this anyway, so I didn't want to do that for you. It's page 385, question 21.14. So I'm going to go through this in the next video. You can go straight onto that if you like, or you can give it a go yourself and then answer question 21.14, whichever suits you.